In this video, we're going to learn about molecular spectroscopy. And here you can see the intensity of radiation that is absorbed by water, by CO2, and by ethanol. We'll come back to this later. So when we think about molecular spectra, we have to talk about what regime we're looking at, because we can get spectra in different parts of the electromagnetic spectrum. Just like with atoms, there are still electrons around the molecule. Now, some of those electrons are shared, but they have energy levels just like they had before. And so they behave in a similar way, but the energy levels are modified by the sharing of the electrons. And so we still get the photons being absorbed or emitted as electrons either jump up or down in energy level. And so we can still look for molecules in the UV. This is kind of an overly cartoonized version. And here what you can see, it's really kind of an electron cloud, and that's kind of changing shape. We get an ultraviolet photon emitted. But we have some other things that can happen with molecules. So here I've got a simple molecule, CO, carbon monoxide, and we can think of them as being carbon and oxygen joined together by a spring. And that spring is basically wiggling. And so when it's wiggling fast, it's got a certain amount of energy. To slow down to a slower vibration, then it has to emit a photon. And so what we get is a similar thing to what we have with the electrons, but now the thing that's changing is the energy in the bond, which is wiggling. Just like with Bohr's atom and the idea of having quantized angular momentum, we apply the same idea here, and this allows us to get a quantization of vibration. We'll come back to that in a little while. But here you can kind of see I've got something that it's wiggling fast, and now it's wiggling more slowly after it's emitted a photon. It's giving off energy and slowing down. And finally, when you have molecules, you can also have them spinning. And so here we have a CO molecule again, and it's spinning. And if it loses some energy, it can now spin more slowly, but to lose that energy, it has to emit a photon. And again, this is going to be quantized, and we're going to get into that in some detail. So let's talk about those rotational energy levels. So basically, when you've got a molecule, if it is polar, then it has a non-zero permanent electric dipole. So you can think of it as being one end is charged positive and the other is negative, just slightly. But if you've got something like H2 or O2 or N2, there is no permanent electric dipole, and so they're going to behave slightly differently. The distribution of charge in CO is enough that as it's spinning, it's basically a charge that is accelerating, and so that is going to give off a frequency that relates to the rotation. So basically what we've got is when we have a polar molecule, as they spin, they give off radio waves. So when we think about rotational energy, let's just go back to a classical model of a rotating thing. So here I've got the equivalent of kinetic energy of half mv squared. What we've got here is the moment of inertia and the angular velocity of rotation. We can also define the angular momentum, which again, just like momentum is mass times velocity. Now, the angular momentum is the moment of inertia times the angular velocity. And if we bring those together, now we've got a relationship between the energy of a rotation, the angular momentum, and the moment of inertia. But as I said, this is just like with the Bohr atom, where we've got angular momentum for the electrons. We're basically going to say there are only certain angular momentums that are allowed. Taking exactly the same idea, we're setting the angular momentum equal to nh over 2 pi, or nh bar, where n is the energy level. And remember that in this case, for rotational quantum numbers, we use the letter J. So here I'm putting this together. I've taken this L is nh over 2 pi, and I've put it into here as L squared, so I've got the h over 2 pi all squared. But here I've put in j and j plus 1 for two adjacent levels, and they're all over 2i over here. This is the moment of inertia. And then if I simplify that, I end up with this equation. So what this gives you is the energy of the state. So this is kind of like with the electrons, where they have a certain energy to be in a certain position, a certain energy level. What they emit is the difference between energy levels, but they have an energy when they're in that level. And this is the same thing, but this is for the rotation. So this is the energy of rotation that is allowed. So here we have that again. We have the energy of rotation, and this is the quantum number for rotation, and this is the moment of inertia. Now remember, what we want to know for detecting the emission is the difference between two levels, right? So here I've got the difference in energy between the second one up from the first one up. So I've got J plus 1 and J plus 2 would be the energy of going up to level 2. J and J plus 1 would be the energy of going up to level 1. And so now we can simplify this. If we simplify this just by multiplying out, we can cancel a few things, the J squareds disappear, and we end up with something that looks like this. And so what we get is an equation that says for a given energy level, that is the quantum number J, rotational energy level, the only thing that dictates the energy levels is the moment of inertia. And that's essentially the distribution of mass. So here's the energy of an energy level. Here's the difference between energy levels, or the photons it will emit. For the ground state, we can put in J equals 0. And what we get is 0 energy. And this is the minimum energy needed to get from the ground state to the first excited state. So let's consider a diatomic molecule. Here I've got a diatomic molecule, different masses on each end. MA is a distance RA from the center of mass, and the total distance between them is RE. What we've got now is they are going to obey the rules for the center of mass. So RA plus RB equals RE, and RA times MA equals RB times MB. Doing a little bit of math, we've got angular momentum is moment of inertia times the angular velocity. And then we can put in the formula for the moment of inertia, which is MARA squared MBRB squared, altogether times the angular velocity. And we can simplify this down. I'm not going to go through the math, but you can figure it out. And we end up with something which is MA MB over MA plus MB. And this is just reduced mass. This is basically, you can substitute this mu value in here, and this is how you calculate that mu value. So now we've got that the angular momentum is given by mu, the distance between the particles, squared, and their angular velocity. The moment of inertia is just mu times the distance between the two. Now, if we have something like hydrogen or oxygen in molecular form, the masses are identical, and so our reduced mass ends up as half m, where m is the mass of a single hydrogen. Here we can then use this into our equation for the radiation that we're going to get. So remember, this is the transition from one energy level to another. And so if we put all of this in, now we've got something where all that really matters is the mass of the particles, that's the two hydrogen atoms, and the distance between them. Now remember that energy is hc upon lambda, so now I can turn this into a wavelength by putting in hc upon lambda equals this transition energy. And if I rearrange it, what I get is this thing. This is the speed of light, pi, Planck's constant. This is the mass of the atoms in the hydrogen or oxygen molecule, and this is the distance between them. So we can work out what wavelengths we should be able to see for each level. Well, this is the E0. This is how much energy is needed to get from the ground state to the first excited state. One of the things that's really important here is that there is an inverse relationship between the rotational energies and the moment of inertia. And so what that means is that for very low mass things, the moment of inertia is low, and so this energy is high. So basically, if the rotational energy needed, that is, if this number is a very low number, making this very high, if that's much, much higher than kT, which is what most of your particle energy is going to be, then you can't collisionally excite to a point where they're spinning at the right rate. And so you cannot get the emission that you want. So for instance, the minimum rotational energy for molecular hydrogen is approximately 500 Kelvin. And that's because of this, because hydrogen is such a light molecule, its moment of inertia is very large. And that's so high that in a lot of places where there's undoubtedly a lot of molecular hydrogen, that we can't see it because it can't emit in the certainly in the rotational frame. But it doesn't mean that we can detect some more massive molecules, and actually a lot of those molecules can be detected down to tens of Kelvin, relevant to some of the coldest places where new planetary systems and stars start to form. There's an implication that we can get from the reduced mass, and that has to do with the fact that you can tell the difference between molecules that have the same chemical composition, but the isotopes of the atoms are different. What do I mean by this? So I want you to consider, I've got carbon monoxide, one of them has a carbon-12, one of them has a carbon-13. The difference in mass between them is only 1 out of 29, but in terms of the reduced mass, it makes a much bigger difference. And so what we have is, here's the mu1, which is for the carbon-12 version. Here's mu2, which is for the carbon-13 version. And the difference between them is enough. It's nearly 5%. And so what that means is that you should be able to see the different energies or frequencies of emission from CO that is mostly made up of carbon-13 compared to CO that's made up of mostly carbon-12. And in fact, you should be able to look at something that has both and be able to tell how much of each you've got. And you can do that for other isotopes too. So we've talked about rotations. Let's take a step back and talk about vibrations now. When you have electrons that are bound to the atom, they are sitting in a potential well. Within that well, you can also have vibrational states. So what we have is a potential well that is where the electron is, and it could be in any one of these states. And then you can have vibrations at different levels, and then you can have rotationals, which are subdivisions of a vibrational level. When we think about vibrations, though, we mentioned this early in the video. Basically, what we've got here is I've got a mass 1 and a mass 2 on the end of a spring, and this is one way for us to model the way that the atom vibrates. And here you can see it has an equilibrium distance here, but if you pull it out, you can then watch how it vibrates, and it's going to vibrate like a harmonic oscillator, so we can understand what we're seeing. When we have a diatomic molecule and it's got a mass on each end, what we care about then is the spring here. And we can think of it as being the potential energy has the form kx over 2, where k is the spring constant and x is how much the spring is displaced from equilibrium. And so what that allows us to do then is work out, well, if there's an integer way of looking at this, you can say, okay, we're only allowed to have energies that are half h bar times the angular momentum. So each energy level is n plus a half times the h bar omega. So that's our quantization that gives us equal spacing in the potential well. So we've got when it's lowest down here, then we have n equals 0 and it's in its ground state. Here we have n equals 1 and the energy is going to be 3/2 h omega. E equals h nu. In this case, I'm using h nu rather than h bar omega. They're somewhat interchangeable since the relationship between nu for frequency and omega for angular frequency is just 2 pi. In this case, nu is the same as for a classical oscillator, so we just apply that to our spring. So here what we've got is an equation for what nu can be in terms of a classical oscillator, where this is a spring constant and this is the reduced mass, but we then have to apply this and say, oh, it's equal to h nu of times n plus a half. So there are different ways that actually the vibrations can happen. So here you can see this is a carbon dioxide molecule. And in this case, you get more complicated wiggling. And so here what we've got is, this is what it is in the ground state. When it's being stretched, here you can see that the stretching is happening so that one side is stretching out when the other side is coming together. It can also be symmetrically stretched, so both move out and both move in at the same time. That's the bottom one. Or you can have something where they're wiggling side to side. You know, there are several different degrees of freedom when it comes to bigger molecules. There are interplays between the different types of transitions. An electronic transition can lead to a vibrational transition, and a vibrational transition can change the rotation too. So you can think of this as being, we excite an electron, and that electronic transition dumps energy, and that's going to affect everything else that's going on. So if molecule has an odd number of electrons, it means that there is going to be hyperfine splitting of the energy levels. And this has to do with the fact that the spare electron has a magnetic effect. When they're paired up, you don't see this, but the extra electron gives an extra magnetic effect. And it's very similar to what we see with the Zeeman effect, where the magnetic field gives rise to fine splitting of the electronic transition lines positions. So this was the image we had at the very beginning of our video. I've got water, carbon dioxide, and ethanol. And you can see here, water, you've got OH stretching and OH bending, and that's giving you some features. These are all in the infrared. This is in microns, so this is around 2.5 microns. This is around 6 or 7, so that's those two. For the CO, this is a CO stretching, and then the CO bending is kind of going off where we can't see it anymore. And then this is more complicated because we've got ethanol, which has carbons and oxygens and hydrogens. So we have OH stretches and CH stretches and COH bending and CO stretches, and you can see there's a lot going on. So as you go to more and more complex molecules, it's going to get more complex in here. Let's finish up by looking at a couple of real spectra of stars. So this is a dusty YSO, that is a young stellar object. So this is something that probably isn't quite a star yet, but has something in the middle that's going to become a star, and it's surrounded by dust. And don't worry about the silicate, we'll talk about that when we get into solid particles. But all of these dips that we see here, those are all due to molecules. So you can see here we've got water, we've got methane, we've got CO2, we've got methanol, got more water, more CO2, more CO. Here we can even see that even in the infrared, and again, this is in microns, so this is 5 and 10 microns, we can see the difference between regular CO2 with carbon 12s and carbon 13 bearing CO2. This is a different type of object in space, and this part of the graph here, you can see this is a real observation of a star called V Cygnus. It's a dusty carbon star. So what we're seeing is actually a whole bunch of absorptions. You can see this is what we think the continuum would be like if we weren't seeing the absorptions that we see due to molecules. And so if we divide by this continuum, so this is basically a black body. You divide by this continuum. So now I've got a flat continuum, and all of these dips that we can see here can be attributed to different molecules. So we've got C2H2, which is acetylene. We've got CO. This is very common in AGB stars, right around 5 microns. We've got methane, and we've got HCN, also common in carbon stars. So you can see how understanding the nature of the molecular vibrations is going to help us to understand all sorts of things that are going on in space. So in this video, we talked about the electronic transitions in molecules that give us UV lines, the vibrational transitions that give us infrared lines, and the rotational transitions that give us lines in the microwave or radio range. We talked about the idea that we're always quantizing these properties. So whether it's the vibrational energy or the rotational angular momentum, there is a quantization. And then we also talked about how in the molecules, we can see the difference between isotopes. And so that gives us another thing that we can use to diagnose what's going on out in space.